Okay, SI-derived units. We said velocity is derived because I'm taking two basic units and I'm having them interact. So length per time, meters per second. Okay, frequency is another derived unit. That's 1 over time, it's 1 over second. It's known as hertz. Volume, that's important. That's a volume. It's a measurement of space where your matter is going to take space. Okay, how do I measure that? I take length in all three dimensions. So let's take this cube that I'm going to draw here. Maybe it's not a cube, maybe it's just, it has different lengths here. So I have this length, this length, this length. Okay? So I can measure this length, I can measure this length, and I can measure this length with a ruler. And I can measure this maybe to be 2 centimeters, and this is 3 centimeters, and this is 5 centimeters, or something like that, right? Then the volume of this prism, as you know from mathematics, would be 2 times 3 times 5, and that's actually 30. So I have shown you here that I have a volume here of centimeters cubed, which is actually a milliliter. That's one thing I want you to take away from this. 1 centimeter cubed is defined as 1 milliliter. Okay, that's one of the definitions, which we use in SI units all the time. We use liters. Okay, so it's just a length cubed. A meters cubed is 1,000 liters, or a centimeter cubed is a milliliter, and that's where it comes from. Right. Density is another one. Density measures sort of like mass, how it's distributed over a volume. Okay, something that's very dense. Okay, if I look at this another box again, something that's very dense is going to have a lot of stuff in this box, right? Very, very dense. If I have another box that's the same exact size, and I have something that's not as dense, maybe it will look like this. Not as dense, meaning this, if I put this on a scale, maybe this weighs, I don't know, maybe this weighs 50 pounds, and this weighs maybe, I don't know, 1 pound. So this is denser because within the same space, I have more stuff. I cram more stuff into it. It's dense. And you can think about that. You take a room and you stuff a whole bunch of stuff in your room. It's going to look so disorganized, so many things everywhere. It's dense. It's hard to get into. If you take stuff out of the room, it's not going to be as dense. Same idea. We derive that with mass over volume, which could be kilograms per meters cubed. That would be the SI unit. Or often it's the same dimensionally. I divide this by 1,000, divide this by 1,000. So kilograms per meters cubed, you can also write that as grams per milliliter. It's the same thing. Okay, so we report density in this fashion as kilograms per meters cubed or as grams per milliliter. Usually you'd see grams per milliliter, which conforms to SI. All right, do I want to do the density? No, I'll do that in a bit when we start doing some other things. Okay. Uncertainty versus is something I want you to discuss here with you. We're going to shift gears to talking about uncertainty and measurements. So this thing called precision and this thing called accuracy. And they sound very similar, and in everyday speech they are. But in science and in engineering, we don't use them interchangeably. There's a particular difference between them. Whoops. Precision says that if I look at a bunch of measurements, so if let's say you go on a scale and you measure your weight, and today it says it's 100, and tomorrow will say it's 100, and the next day it's 100, and the following day it's 100. Okay, that means that the measurements are very precise. They're very close together. If I look at the average of all your measurements, all your measurements fall within a very close, narrow range to that average. Accuracy is a different issue. So let's say your weight is actually 200 pounds, but you want to lie to yourself, so you change the scale so that it reads 100 instead. So your scale is going to be very precise. It's going to tell you 100 every day, but it's inaccurate because you're actually 200 pounds. So accuracy talks about how close something is to the real value. Precision talks about how close the individual measurements are. So accuracy is how close measurements are to the real value. And precision is how close individual measurements are to one another. And I think that warrants an example. Why not? Let me find it. I just wrote it down before, so we have it. Great. So let's say, okay, I gave 3 of you a paper clip, and I know my paper clip. I love it. The mass of my paper clip is my best friend. I measured it tremendously, and I know this. It's true as gospel. It's 3.2 grams. All right? The mass of my paper clip is 3.2 grams. You cannot deny that. That is given truth. Universal value. All right. Now, I give you the paper clip, and I ask you to measure it. So let's look at some measurements. I said, put this on a scale and measure it. That's all. And I give it to 3 of you. So I have student A, and this is their measurements. I have student B and then student C. Student A measured, let's see, student A measured 3.1 and then 3.15 grams, all in grams. 3.13 grams, 3.17 grams, 3.1 gram again, maybe 3.18 grams, and then 3.2 grams, okay? So, is this precise? Well, yeah. They're all very close together, aren't they? So this is precise. So I will note this as precise. Precise. Is this accurate? Well, yeah. My value is 3.2. They're all close enough. So I'll say that this is also accurate. So this is great. This student A should get 100. She's very smart. She can put a paperclip on a scale. So that's one way. Student B got these measurements. 4.1, 5.2, 6.3, all grams. 3.0. I'm just omitting the unit, but it's all grams. 1.1, 1.2, 1.5. Okay, so these are all grams. Grams, 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 grams. Okay. Are these precise? Well, no, because they're not close together, so they're imprecise. Are these accurate? Well, no, they don't. Not even close to 3.2. 3.2 is the universal truth of my paperclip. This person is imprecise and inaccurate. That's not good. This person doesn't know how to weigh things on a scale. So S and F for B. And then C, student C measured this. Again, all in grams. 7.2, 7.2, 7.1, 7.1, 7.2, 7.0, 7.0. All grams. G, 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 G. All right. Is this accurate? No. No. It's like double the weight. So no, this is not accurate. So this is inaccurate. Is this precise? Yeah, that's precise. The values are all close together. This is precise. Okay, so hopefully this kind of shows you what the difference is. Now, why do I care? Here's why I care. Here, I don't think the person did anything wrong. I think the scale lied. I think something is wrong with the scale. We have to get a new scale or calibrate or do something to it. Something is wrong with the scale, but it's giving us precise measurements, meaning that you can maybe calibrate it and trust it or something. Here, I got the true value and it's precise, telling me the scale is good and I'm getting good values. Great, so I can actually get meaningful things out of the scale. Here, this scale is terrible, unless either the measurer is terrible or the scale is bad. One of those two is bad. Something fishy is going on here. So I can actually weave a story out of this and be able to understand measurements better.